Today we will study about motion in higher dimensions. This topic can also be called as general motion in a plane or motion in two dimensions. Whatever I am discussing today is true for motion in two dimension also. It is true for motion in three dimension also. Or if you want, you can generalize it to for motion in any n dimension. But when we are discussing motion in two dimension or in three dimension, we have to discuss how to define the position of the particle. So suppose I have been given a particle here P, then in order to define the position of this particle in two dimension, suppose this is the position vector r is equal to xi plus yj, so I can write it as this is sum of two vectors xi plus yj. So the position of any particle in two dimension, or for that matter in three dimension, can be denoted by r, and this r is equal to xi plus yj. Now after finalizing the position of the particle, since we are dealing with the motion of the particle, the position vector will change. So initially suppose the particle was at this point p1 at time t1, say from this point it moves to this point p2 at time t2. So the initial position vector is r1, finally the position vector has become r2. This is my final position vector. So at time t1 the position vector was r1, at time t2 the position vector is r2. So displacement in this time t1 to t2 is given by displacement vector delta r is equal to r2 minus r1. The same thing I can write in x and y terms also. So it will become delta r is equal to r2 minus r1 is equal to x2 minus x1 I is the unit vector in this direction and j is the unit vector in this direction, plus y2 minus y1 j. So x2 minus x1 I can write as delta xi plus delta yj. Suppose this motion is going on in three dimensions. So in addition to I and j, I will have a k component also, and this will become plus delta z in k. Now that we have found displacement vector also, next goal will be to find the average velocity and the instantaneous velocity. Now the average velocity will be the rate of change of this displacement vector delta r. So at time t1 the particle was here, at time t2 it is here, so it has changed from position vector r1 to r2. So the displacement vector is delta r, so average velocity will be delta r by delta t. The same thing if the delta r I write in terms of x, y and z component, it will become delta xi plus delta yj plus delta zk whole divided by delta t. So this will be the expression for average velocity. Now in order to find the instantaneous velocity, we will take the limit of this average velocity as delta t tends to 0. So instantaneous velocity is defined as limit delta t tends to 0, delta r by delta t is equal to dr by dt. Now when you do dr by dt, your r is xi plus yz, r is this vector. So when you differentiate, you will get dx by dt I plus dy by dt j plus dz by dt k. So this will become v is equal to vxi plus vyz plus vyz plus vzk, where vx is equal to dx by dt, vy is equal to dy by dt, and vz is equal to dz by dt. This is very simple. This is simple generalization of all the formulas, all the expression we had in one dimension. We can generalize it to two or three dimension. Similarly, what will happen here is, suppose this was the path my particle was taking, the dotted curve. Initially at time t1 it was here at a, and say at time t2 it was here at position b. So this line, the black line, was giving me the average velocity. Now as this delta t tends to 0, that is the time interval between t2 minus t1, as it goes to 0, what happens? This point b1 starts approaching this point a along this curve. So from b it will go to b prime, then it will go to b double prime. So ultimately it will approach this point a. So when it approaches this point a, these secant line, this one, this one, this one, ultimately this sequence of secant line will become this green tangent line, and this green tangent line is the direction of instantaneous velocity at that point A. So at the end point as the end point approaches A, delta t approaches 0 and the direction of delta r approaches that of the green line tangent to the curve at A. So this green line gives me the instantaneous velocity at A. If I write this velocity in terms of x and y components, so this velocity is v is equal to vxi plus vy z. Suppose this velocity vector is making an angle theta with horizontal, so your vx will become vx is equal to v cos theta, vy will become vy is equal to v sin theta. So I can write the magnitude of v will be vx square plus vy square, and this angle theta will be given by tan inverse vy by vx. After finding velocity, let's see how to calculate acceleration. So for acceleration also we will have one term called average acceleration. So what is average acceleration? That will be v2 minus v1 by delta t, that is change in velocity divided by time, that is delta v by delta t. In order to find instantaneous acceleration, I will take limit of this expression, limit as delta t tends to 0, so I will get a is equal to dv by dt. If I write it in terms of vx and vy component, I will get a is equal to d by dt vxi plus vyz plus vzk. So when you differentiate dvx by dt, you will get ax, this will be ay and this will be az. This is the graphical representation of average acceleration. Your velocity at point 1 was v1, at point 2 it is v2. So the delta v will be v2 minus v1. So this is the direction of your average acceleration. For finding instantaneous acceleration, this is the instantaneous velocity. You differentiate this vector, you will get instantaneous acceleration in this direction. Till now we were discussing motion in a plane or motion in higher dimension using rectangular coordinates, that is x, y, z coordinates. Now there are another set of coordinates which are very helpful when we are dealing with motion in a plane. Now suppose instead of describing position of this particle using x and y coordinates, if I say that okay, let's take a unit vector in this direction, in the direction of this position vector itself. So I will make my unit vector in this direction. Say let's call this as my unit vector, and obviously this is the magnitude of the position vector. So I can write my position vector as r is equal to r. This r is, whenever there is no vector sign, it means this is the scalar, this is the magnitude of this length or magnitude of the position vector, multiplied by this r cap. This r cap is the unit vector in this direction. So I can say that I can describe my particle using this notation also, because in this notation the position vector is equal to r. This r is the scalar magnitude of the position vector multiplied by unit vector in this direction. So I can describe my particle in this notation also. Now in this notation there are 5 points you have to take care. First of all, you will say ki okay, you have described your position of your particle using this r is equal to r into r cap. Then you may wonder that since we are describing motion of a particle in 2 dimensions, and you have been told earlier that when you are describing motion in 2 dimension or position in 2 dimension, you need 2 vectors, 2 unit vectors, x hat or ij. When you are dealing in 3 dimension, you need ij, k also. So you can say ki in this notation this is a very simple notation, and this r hat or r cap, how come only one unit vector r cap is describing the position of when your particle is here at this point P, and this is my r cap. So I can write r is equal to r cap. Now the moment suppose your particle goes here, it is at this point or at this point, your r cap has changed. Your r cap will be in this direction. So ultimately, so eventually what is happening, this r cap itself depends upon theta. So if I expand it, and I will show in next slide that this r cap can be written in terms of I and j also. So this r cap, the unit vector, it is not like this I and j unit vector. The I and j unit vector are fixed in direction, that is, it is always in the direction of this x-axis and y-axis. But this r cap vector, this is moving along with the particle. So when your particle is here, r cap is in this direction, in this angle theta direction. If your particle goes here, your r cap will be in this direction. So the direction of r cap, this unit vector has changed. So this unit vector is also called radial unit vector. It is very special kind of unit vector. It is unit vector because its magnitude is 1, granted, but its direction is changing. It is changing with the motion of the particle. So when my particle P is at this location at a distance r and at an angle theta from x-axis, this is r cap, and I can write my position vector as this. Okay. Now this position vector depends upon r also and depends upon theta also. So don't be confused that how come I can define or how come I can describe position of a particle in 2 dimensions using only one notation r. This r denotes the length of this vector or the magnitude of position vector, but this r cap, it depends upon, it is a function of theta. It depends upon theta. So your total position vector, this r, depends upon scale, this magnitude also, and it depends upon theta also. Therefore this position vector given in terms of r, the scalar magnitude, and r cap depends upon both this r and the theta. And since for describing motion in 2 dimensions we need 2 unit vectors, like for x and y axis we were having a combination of I and j. In this case, since we have finalized one unit vector in this direction r, let's finalize another vector theta cap in this direction, because normally it's always convenient to take a pair of unit vectors which are perpendicular to each other. So I have taken another unit vector, this theta cap, and it is called tangential unit vector, which is perpendicular to this r cap. So I will show that using this r cap and this theta cap, I can describe the position. Obviously position can be described without taking help of theta cap also, but for describing velocity and acceleration I will take help of both this r cap and theta cap and describe the velocity and acceleration of the particle when the particle is moving in a plane. Now let's give a full-fledged expression of this r cap and theta cap in terms of this angle theta. Suppose my particle P is here. What is this r cap? This r cap is a vector, radial unit vector in this direction. So if this angle is theta, this angle will also be theta. And this violet line I have drawn, this is for my I-axis, this is the unit vector I, and this is the unit vector j. Why I can say they are I and j? Because this vector I is parallel to x-axis, this is my x-axis, this is my y-axis, and j is parallel to y. Okay, so this green line is my r cap. So when I have to write r cap in terms of I and j, I will draw a perpendicular here. Since this is theta, this, what will be this? This will be cos theta, and this will become sin theta. So I can write r cap is equal to this I, what is this much? Cos theta times I plus sin theta times j. This is my r cap in terms of I and j vector. Similarly, this is my theta cap. In order to find theta cap, you see this angle between r cap and theta cap is 90 degree. So obviously when I draw a say horizontal here, this angle will be 90 minus theta. So this will become this line, this length of this will be sine of 90 minus theta, that is cos theta, and obviously this thing will then become sin theta. And since this is going in minus direction, so I can write my theta cap will be minus sin theta I plus cos theta j. Okay, so these are my unit vector r and unit vector theta, that is the radial unit vector and the tangential unit vector. R is cos theta I plus sin theta j, and theta cap is minus sin theta I. Why minus? Because this theta cap at this point is going in backward direction or leftward, so that's why minus sin theta I plus cos theta j. Now you can also see that this r cap dot theta cap is equal to 0. Why? Because when you take the dot product, this will become minus cos theta sin theta plus sin theta cos theta, so their dot product is 0. It means these two vectors r cap and theta cap are perpendicular to each other. Okay, so this angle is 90 degree. In fact, it was 90, it had to be 90 degrees because we had constructed this theta cap in such a direction that the angle between r cap and theta cap was 90 degree. Now after doing this, now that we have finalized my r cap and theta cap, we have to find out the time derivative or the derivative of these two vectors, like dr by dt. What will be the derivative of this vector with respect to time? Similarly, what will be d theta by dt? Now you can say, why do you need dr by dt and d theta by dt? We need them because we have to find velocity vector and acceleration vector, and when we are finding velocity vector, we are differentiating position, and in that position this r cap is there. That's why we need this dr by dt. Another thing, you can say, why do you need this? When we are writing my position vector in terms of this I and j, that time we were not worried what is di by dt and what is dj by dt. Of course we were not worried because these are constant vector. I and j are constant vector because their direction is constant. You see, this r cap and theta cap are also unit vector, so their magnitude is constant, but their direction are changing because these vectors are dependent upon cos theta and sin theta. So as the theta changes, their direction of these r cap and theta cap also change. Therefore we need to find dr by dt and d theta by dt. Before that, let's discuss a concept of time derivative of vector. Now suppose you have been given a vector, say a, and you have to find derivative of this vector dA by dt. Okay, now see, vector has got two things. It has got magnitude, and it has got direction. So if any of these two things, if they change, the vector will change and I will have a dA by dt vector. So if magnitude is changing, then also I will have dA by dt. If the magnitude of a vector is constant, but if the direction is changing, even in that case I will have dA by dt, as is the case with this, say, r cap and theta cap. Their magnitude is constant, is equal to 1, their magnitude is 1, but since their direction are changing, I will have dr by dt and d theta cap by dt. So in general, if a vector a is given, and if suppose both the magnitude also and the direction also are changing, then dA by dt will be in arbitrary direction, suppose in this direction, dA by dt. Now suppose I have been given a vector, say a, and it is also given that the magnitude of a is constant, that is the magnitude is not changing. Then what can I say about dA by dt, that is the derivative of this vector with respect to time? Since magnitude of a is constant, it means magnitude of a square is also constant, some constant c square. Now I can write magnitude a square as a dot a. Now this is constant, so this is c square. When I differentiate both sides, LHS and this, when I differentiate this, I will get 0. Why? Because differential of any constant thing is 0, so let's make this whole thing 0. Use the chain rule, so it will become a dot dA by dt plus dA by dt dot a is equal to 0. Since the scalar dot product, they are commutative, so whole thing I can write as 2 times a dot dA by dt is equal to 0. I can remove this 2 also because it is of no use. So what I have found out, that when magnitude of any vector, be it position vector, velocity vector, acceleration, whatever, magnitude of any vector, if it is constant, then this derivative dA by dt has to be perpendicular to this A. Why? Because these two vectors are non-zero. Suppose this A is also non-zero vector and dA by dt is also non-zero. I am assuming that there is some change. If you have dA by dt itself 0, then that is a trivial case. So I am discarding that case. So if your A is non-zero vector, dA by dt is a non-zero vector, but their dot product is 0, it means these two vectors are perpendicular to each other. So I have proved that if the magnitude of any vector is constant, then its derivative has to be perpendicular to the direction of that vector. So suppose this is a vector A whose magnitude is constant. Now that the magnitude is constant, what can I say about the direction of dA by dt? It has to be in this direction, perpendicular. It has to be perpendicular because suppose you have dA by dt in this direction. Suppose you have a dA by dt in this direction, then what will happen? Because this is dA by dt, then a component of this change, that is this dA by dt, will be in this direction and it will try to pull out this vector, that it will try to increase the magnitude of this vector A, which contradicts the basic assumption, the basic premise of the problem, that this is a vector of constant magnitude. Similarly, dA by dt cannot be in this direction. In circular motion, radius is constant, that is r is equal to constant modulus of r. So since radius is constant in circular motion, the velocity vector has to be tangent to the position vector, and position vector is given by the r vector. So everywhere you see it will be tangent. Similarly, suppose if the circular motion is uniform, that is modulus of v is also constant, some other constant c1. So in this case, what I can say, v dot dv by dt is equal to 0. So this dv by dt, that is acceleration, that has to be perpendicular to velocity. So since velocity is in this direction, my acceleration has to be either in this direction or in this direction. Ultimately we will prove subsequently that it is inside. So acceleration is also towards center, or it is perpendicular to the green velocity vector. So you see what happens, the instantaneous velocity is tangent to the circle at all points. Why? Because of mod r is equal to c, radius is constant. Similarly, since in uniform, for uniform circular motion, mark the word uniform, if the circular motion is not uniform, if that is, if velocity mod v is not equal to constant, it is changing, in that case your acceleration, total acceleration, will be in different direction, not in this perpendicular direction. But for uniform circular motion, the acceleration a points to the center of circle. Why? Because this v is tangential, so a has to be perpendicular. So you can say it can be this direction also, this direction also, but ultimately if you find change of v, that is towards center, therefore it is in this direction.